Question 2. This question is about elements with atomic numbers between 58 and 70. So a bit of the periodic table you don't often look at. Cerium, atomic number 58, is a metal. Complete the table to show the relative charge of each particle, the number of each particle found in the cerium 142 plus ion. Okay, so this one is similar sort of thing to the first question, but this time you've got an ion to contend with as well. So the 140 here is the atomic mass of this cerium isotope. It's a 2 plus ion, which means it's lost 2 electrons to give us a 2 plus charge overall. Relative charges on each particle. So 1 mark for the first column. So protons have a relative charge of +1. Neutrons obviously have got no charge at all. They're 0. Electrons are -1. So a word of warning on this column, you have to make sure whenever you're referring to relative charges of the particles, you've got to give symbol and number. +1, not just 1 on its own, not just a plus on its own. It's got to be +1, and likewise the electron has got to be -1. Okay, so number of each particle present in the cerium 142 plus ion. Well, it's a cerium particle, cerium atom, so the number of protons will be the same as the atomic number of cerium. We're told that in the question is 58. So we know it's going to have 58 protons. If we jump to the electrons next, because we can do that much more quickly, it's a 2 plus ion, which means it's lost 2 electrons, so it's got 2 fewer electrons than the number of protons, so it will have 56 electrons. Number of neutrons then is going to be 140, take away 58. All right, just to make sure we get the right answer here, 140 minus 58 gives us 82. Part B. Cerium behaves as a typical metal when it reacts with dilute sulfuric acid to form the salt cerium-3 sulfate. You've been given the chemical formula, and hydrogen gas. Now remember, hydrogen gas is diatomic, so it exists as H2. State the formula of the 2 main ions in the solution of cerium-2SO4-3. So, start with the cerium. We're given the Roman numeral there, 3. This tells us the charge on the cerium ion. So it's not the same as this one. It's a different one. This is cerium-3, so this one will be Ce3+. All right, the Roman numeral is the indicator in terms of the charge, and metals always lose electrons, so metals will always become positive. Therefore, the other one is the sulfate ion. This is one of the ones that you need to learn, you need to remember. It's SO4, 2-. Right, a balanced equation for the reaction of cerium with dilute sulfuric acid. You need to know your acid formulae. You will not be given them at this level. At GCSE, you're always provided with your acid formulae. At A level, you won't be. So sulfuric acid is H2SO4. Make sure you're going through your acid formulae and committing them to memory. So, equation is cerium plus sulfuric acid. It tells us that we're forming the cerium sulfate and the hydrogen gas. We've got the formula of the cerium sulfate, Ce2. SO4, 3, and hydrogen is H2. Okay, any acid plus metal always produces a salt and hydrogen. It's a basic equation for an acid-metal reaction. We need to balance the equation out. I've got 2 ceriums here. Let's put a 2 there. I've got 3 sulfates, 3 lots of SO4. So I put 3 sulfuric acids. That balances out all the SO4s there. And now I've got 3 times 2 is 6 hydrogens. So I put a 3 there for the 6 hydrogens. So it's 2Ce plus 3H2SO4 will give you Ce2SO4 3 plus 3H2. Question C. Europium, atomic number 63, reacts with oxygen at room temperature. Calculate the mass of europium oxide that can be made from 9.12 grams of europium at room temperature and pressure. Okay, we've got a slight problem with the answer line. This was a misprint. When I designed the paper, that should read mass rather than volume. So it's mass in grams, so don't let that be confusing to you. So I've got a mass here of europium. I can use the mass to work out the number of moles of europium. I can use my equation to work out the number of moles of europium oxide by looking at the ratio and the balancing. And then from there I can work out the mass of the europium oxide that forms. Now the most common error I've seen with this question time and time again, students see the 63 there and use that number instead of the atomic mass. This is the atomic number of europium. This is the number of protons. You can use this to help you locate it on the periodic table quickly and then find the atomic mass. So be careful that you're using the right numbers. So we start off here with moles of europium. It's mass over molar mass. The mass is 9.12. The molar mass of europium, if we look for atomic number 63, and europium has got an atomic mass of 152. So 9.12 divided by 152, first of all, put the calculator in. 9.12 divided by 152 gives you 0.06 moles. So that will be your first mark for this 2-mark calculation for working out the number of moles of europium. I've then used the ratio here that 4 moles of europium will produce 2 moles of europium oxide. Therefore, 2 moles of europium will produce 1 mole of europium oxide. We've got 0.06 moles, so we're going to produce half the amount. So 4 to 2, 2 to 1, 1 to half, 0.06 to 0.03. Okay, so moles of EU2O3 is 0.06 over 2, which is 0.03. You don't get a mark for that one. All right, that's just leading you into the next bit. So last bit then is now using this number of moles to work out a mass. So I'm rearranging my equation. We know that moles equals mass over molar mass, and mass therefore is Mr. Moles, Mr times moles. So this is my mass now of the europium oxide, the EU2O3. Let's put that there to make it clear. So the Mr of europium oxide, we have to work this out from the figures given here. So we know that europium is 152 and oxygen is 16. So I'm going to have 152 times 2, which is 304, plus 3 lots of 16, which is 48. So the atomic mass of europium oxide is 352. Sorry, the Mr is 352. Times by 0.03 will give us our final answer, which is 10.56. Okay, 3 significant figures in the question, so 10.6 is a correct rounding there. If you want for 10.6, that's fine as well. Okay, part D. This question is about compounds used as fertilizers. A compound used as a fertilizer has the following composition by mass. So we've got there the different elements present and their percentage composition. State what is meant by the term empirical formula. Another definition, 1 marker. You've got to get some keywords in there again to make sure you get that mark. All right. Empirical formula, simplest, must mention that word. Whole number ratio of atoms. Again, it's atoms, not elements or anything else, in a molecule or in a compound. You've got to say where it comes from. All right, so if you want to get that mark, you need to make sure every word is mentioned there. Simplest whole number ratio, atoms, molecule. That's all, atoms in a molecule. Okay, now we need to calculate it. So whenever you're faced with your empirical formula calculations, the best way to attack them is to try and do like a tabular method. So what I always do is put my 4 elements at the top, C, H, N, and O, and then write their percentages underneath, because we're going to use the percentages instead of the masses. It can be used in exactly the same way. So 6.67 for hydrogen, 46.67 for nitrogen, 26.66 for oxygen. And just like you calculate moles up here with mass of a molar mass, you can do exactly the same with your empirical formula and use the percentage by using the percentage over the molar mass. All right, all we're assuming is that we've got 100 grams. It doesn't make any difference at all. So divide all of these then by their atomic mass. So carbon has got an atomic mass of 12. Hydrogen is obviously 1. Nitrogen is 14. Oxygen is 16. Okay. This then gives us a number of moles for each of them. That alone will get you your first mark. Just doing that showing that division, and or actually physically calculating them, but either way you get your first mark just for doing this bit. Okay, so let's bring the calculator back in. 20 divided by 12. It's 1.667. Okay, 6.67 divided by 1. Is obviously 6.67. 46.67 divided by 14 is 3.333 or 3.334. And 26.66 divided by 16 is also 1.666. Okay, so very similar to the carbon. So that's your number of moles of each one. You then divide by the smallest. The smallest here is 1.666. So we divide all of these by the same value, the smallest number. So I'm going to put an arrow across because it just means I'm dividing 1.666, or all of these numbers by the same value. Okay, I've got a lot of room here, so let's just go underneath the answer line just for now to give us our ratio then. So obviously that's going to be 1, and the end one's going to be 1 as well, because we've got it dividing by itself. So if we do 6.67 divided by 1.666, that gives me 4, with 4.0, and the same here, 3.33. 4 divided by 1.666 gives me 2. And there's my ratio then. And it is all whole numbers, so I haven't got to do any scaling or anything. Remember, you can't round with these questions. So my answer is CH4N2O. Put on the answer line, CH4N2O for your second mark. So first mark is for either the first bit of the calculation, the workings here, or for your actual answers, moles. And your second mark then is for your final answer. Question E, potassium is a common element found in fertilizers. State the number of electrons in the 4th shell of potassium. All right, so if you're not sure on this one, let's write the configuration for potassium out. It's 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. 4th shell, only 4 there. It's 4s1, therefore it's 1 electron in the 4th shell. It's the outer shell. All right. State the number of orbitals in the 3rd shell of potassium. The number of orbitals in the 3rd shell of potassium. Okay. With the 3rd shell, we can see we've got an S subshell and a P subshell. An S subshell consists of 1 orbital, and a P subshell consists of 3 orbitals. So there are 4 orbitals in total in the 3rd shell. The answer is 4.